All right, ultrasound physics in an hour. This will be a challenge. First of all, you know, when I first started doing some radiology physics lectures when I was a resident at Washington University in St. Louis, and I continued to do them as a fellow, and then when I stayed on staff. And I didn't have an ultrasound lecture as part of that. And one of the residents who was a few years behind me, Lance Rhinesmith, actually said, hey, I'd love to do an ultrasound lecture do you mind if I join in on the physics reviews you're doing? And so Lance actually wrote the first version of this talk, and I've modified it, adapted it since then, so I certainly want to give him credit for that. So let's talk a little bit about acoustic waves, right? Because they're fundamentally different than the electromagnetic waves we've been talking about in all the X-ray imaging modalities, and in addition to the, electromagnetic radiation that you guys talked about when Dr. Serlin talked about MR physics. Because this is truly a mechanical wave, right? It needs a medium through which to propagate. And humans can detect frequencies kind of in that 20 to 20,000 hertz range. Ultrasound imaging, we're really working transducers that are in that kind of megahertz range, which is why we use the term ultrasound to describe that. Right, so the pressure changes from vibrating molecules are transferred mechanically to those neighboring molecules by a process called propagation. So when I speak and create sound, it's not that the air molecules at my mouth are traveling out to you guys, and instead the air molecules are moving back and forth, and that is propagated to adjacent air molecules out there to ultimately vibrate some of those molecules adjacent to your eardrum, and you're hearing the sound I'm speaking with. And that process requires an elastic medium, right, unlike electromagnetic radiation. And that can be a solid, it could be a liquid, or a gas, and those media propagate sound slightly differently. So here's a good picture, right? If you take a look at a speaker and you think about what happens at the diaphragm of that speaker as it pushes out and pulls back in, it's really compressing some of those air molecules closer together, and then as it pulls back, it's separating some of those, and that pressure wave moves forward through the air. And if we could look at what's happening in the air, we'd see successive areas where air was compressed together, and then areas where air was more separate, molecules were separated from each other. So these areas of compressions and rarefications. And so if you think about that, you can kind of look at that, how densely packed together they were, and look at that sinusoidal nature, that time-varying nature of that. So some basic nomenclature. We're already familiar with these because we've talked about waves when we were talking about electromagnetic spectrum, but the wavelength is the distance between two areas of compression, or if you will, between two areas of rarefication. The frequency is the number of cycles of that we've got per unit time. And the acoustic velocity, that's the speed at which that sound wave is propagating through the particular medium of interest. The amplitude, the magnitude of that sound, when I make the sound is louder, that really has to do with how many of those air molecules were getting packed together, how densely packed together they are at those areas of maximum compression, if you will. So what determines how quickly sound moves through a particular media? Well, one of the things is the material's density, and in general, the more dense a material is, the more it impedes sound propagation. So more dense materials tend to not propagate sound as quickly. But countering that is compressibility. So the more compressible something is, the more it impedes the propagation of sound. Or if you will, the less compressible something is, the more easily sound travels through that. And there's this thing called the bulk modulus, which is the reciprocal of compressibility. In other words, it really measures how stiff something is. So the more stiff something is, the more quickly sound will propagate through that. So all other things being equal, increasing density would decrease acoustic velocity, and increasing compressibility would decrease acoustic velocity. Or I could say this last statement another way, right? increasing stiffness would increase acoustic velocity. And that gets to this one, right? When I first said, well, sound travels slower in things which are more dense. You probably said, well, wait a second, I thought sound travels faster through solids typically than it does through air or liquids. And that's because while those variables are independent from each other, increase in density often change that speed less than the decreases in compressibility or the increase in stiffness. So the reason that sound tends to travel faster in solids is because they're much less compressible, even though they're more dense, okay? So that compressibility plays a bigger role in why that's happening than the density, okay? All right, so let's take a look at a few things in just a table of how fast sound travels through a media. And I've circled a bunch of things here. And if you even take a look at water and at mercury and aqueous humor, vitreous humor, you'll notice that a lot of these really fall in a very similar range to each other. For instance, mercury is about 11.6 times more dense than water. So, well, by applying that, we say, well, sound should travel slower there. But it turns out that water is about 13.4 times more compressible than mercury. So their acoustic velocities are actually fairly close to each other. And that's true for a lot of materials. And that's very helpful to us because in the soft tissues where we're going to be imaging, we're going to assume that sound travels at a fixed rate, no matter what that is, whether we're in liver, whether we're in blood, no matter what the soft tissue material is. And that isn't exactly true, right? You can see that the speed in liver is slightly different than it is in muscle, than it is in fat, than it is in blood here. And so that will sometimes give rise to a few little artifacts that we may see on our image, but in general, it's a pretty close approximation. And that's what makes imaging with ultrasound possible for us, because really all we're going to do is we're going to send out a pulse of sound, and we're going to listen for that echo to return back to the transducer. And when we hear an echo strike back at the transducer, we're going to plot a pixel at the depth at which that echo must have been produced. Well, how do we know that? We assume a constant velocity for the sound. We take the time that it took the echo to return to us, and we can easily convert that to the distance at which that echo must have been produced. And we can make the pixel of varying brightness depending upon how strong the echo was that we heard back, okay? We'll get into that more as we talk about making the images. So, in fact, most soft tissues and liquids behave such that the density and compressibility cancel each other out, and those velocities are very similar. So we're going to use this number, right? 1,540 meters per second. Not a particularly useful number, right? I've never imaged a meter deep in a patient, so I often kind of remember this more as what we can look at dividing both of these by 1,000. So if we divide meter by 1,000, we get a millimeter, and then per millisecond, right? So you can also remember this in terms of 1.54 millimeters per millisecond, right? Which is oftentimes comes in a little more useful for the depths that we're going to image in a person. Temperature does play a little bit of a role on how fast sound travels in the body. It's really not going to be that important to us, but for just in terms of learning purposes, the speed of sound does increase in higher temperature. So let's think about just a single medium now, because we talked about, yes, sound does vary some different speeds in different media. We're going to assume it's mostly the same in soft tissues, but let's talk about a single media. So we know that the speed of sound is equal to the frequency times the wavelength. That acoustic velocity is the same throughout one medium, and thus the wavelength is inversely proportional to the frequency. So no matter what that velocity is, since that velocity is going to be the same, if I vary the frequency of the transducer, the wavelength of that ultrasound probe pulse has to vary. So what if I go from a 5 megahertz frequency ultrasound wave to a 2.5? Well, of course, if I drop if I go from 2.5 to 5, that's twice the frequency. The wavelength is cut in half, right? That relationship is just given by that simple equation using the fact that the speed through that, the velocity through that tissue is the same for both of those. We like using the highest frequency possible because that really gives us the best axial resolution, the best resolution along the direction that the X-ray beam is propagating. The problem that we'll see as we go a little deeper is the higher the frequency we go, the more the sound beam is attenuated as it goes into the material. So it really restricts how deep we're able to image into the tissues there. So we're assuming that that acoustic velocity is similar, that 1540 meters per second in most of the soft tissues, and using that and applying that into the equation where now we know the velocity, and so we've got the frequency times the wavelength. It allows us to calculate what the wavelength is, again using that this simple formula, 1.54 millimeters divided by the frequency of the transducer. Now, what happens if we cross across two media? Now, I told you that in soft tissues, we're going to assume that these velocities are exactly the same, right? But that isn't really true. And so in terms of crossing two media for a little while, let's look at what really happens, right, where those velocities are slightly different. So if the wavelength is so that frequency remains constant. So that wavelength is going to have to vary in that case. So setting these two things equal to each other, if that frequency stays constant, we've got the wavelength in soft tissue, and the wavelength, we've got this 2.5 megahertz transducer with a wavelength of 0.62 in that soft tissue. What's the wavelength when that beam travels into bone, where the speed of sound is quite different, right? Because this is now not a soft tissue material. This is a much stiffer, less compressible tissue. The speed is 80 meters per second. Well, just using the formula that we have right here, putting in our 1540 and our wavelength for that sound wave in soft tissue, our 4080 for bone, and for calculating what that wavelength is in bone, we'll notice here that that wavelength is quite a bit longer there. So the intensity of the sound beam is the rate at which the energy is transmitted by the sound over some small unit of area, right? Increased intensity means that the particle oscillations increase and those maximum particle velocities are also increased. So frequency, wavelength, and acoustic velocity of the beam, they're not affected by a change in intensity of the beam if the beam propagation is linear. So intensity is really independent of those if propagation is linear. It turns out propagation being linear is a decent approximation in soft tissues, not quite true. So we really can view these as kind of being independent of each other. So we can vary our frequency and that intensity of that beam independently of each other. The next thing I want to mention is when we talk about the intensity of sound, right, the number of those air molecules that are on that wavefront of compression that may be pushing on your eardrum as that sound travels to you, we measure that in a relative scale. So the intensity striking your eardrum divided by the original intensity, and we use a logarithmic scale for that, 10 times a log base 10, and this is referred to as a decibel. So we measure sound intensity typically in decibels. Of course, we're not listening to the sound in ultrasound, but the setting on the ultrasound transducer that's controlling how intense the transmitted waveform is that gain knob, right? As we turn that gain knob up, we're creating a more intense ultrasound wave that's going to be propagated into the tissue. The total power is the total energy transmitted per unit time, or if you will, the intensity, summed over the entire cross-sectional area of the ultrasound beam. So it's that intensity over the area. And I mention this just to remind you that when we do ultrasound imaging, we deposit energy into the tissues. As a matter of fact, some therapeutic uses of ultrasound take advantage of this, where they're really trying to heat the tissue by depositing energy there. We typically don't want to be depositing energy, or certainly don't want to be depositing much energy, and there's certain applications, such as in neonatal imaging, right, where we really want to be careful that we're not imaging the embryo with too much power early on. So we've talked about these ultrasound waves. They're now propagating through these tissues. As they propagate through, they're going to interact with them. And they're going to interact in some ways that, you know, the names are quite similar to how we talked about X-ray interactions. But these are true mechanical waves, so they're going to behave somewhat differently in some respects. And I want to talk about some of the different ways they interact. I want to talk about reflection. I want to talk about scatter. I want to talk about refraction. I want to talk about diffraction, interference, and absorption. So reflection. You know, sound, as it strikes some surface at a particular angle, you end up with a significant proportion of that sound reflected off oftentimes, and some of the sound gets transmitted through that, and we'll talk about that transmission later. But this angle of reflection is equal to that angle of incidence, and this occurs at interfaces that are quite smooth. Okay, they're referred to as specular reflectors. In some ways, they act as a little bit of a mirror, if you will, kind of with that sound. So here's a nice specular reflector, and if we're at 90 degrees to that, then some of the sound passes on and transmitted. We'll talk about that. And then, but some of the sound gets reflected back towards the transducer. The bad thing with specular reflectors is if you're not at exactly 90 degrees with respect to the interface, that sound wave comes forward, some transmitted and some reflected, but the angle of reflection is away from the transducer. So when we want to see these specular reflective surfaces well, we've got to get the transducer nice and perpendicular to them. And I'm a bone and joint imager, right? So this is especially problematic for me, right? If I want to see these interfaces in the deltoid musculature, or certainly in the supraspinatus tendon, I really want to make sure my transducer is perpendicular to the surface of those. As the ultrasound beam starts to be more obliquely oriented with respect to those linear fibers of those tendons or those muscles, I don't see them nearly as well. Not because there's something pathologically wrong with them, but because the sound is being reflected away from the transducer. So we've got to keep that in mind. These provide the really nice boundary image information that we see on images. As everyone see, we can see the sub-Q fat so nicely, the boundary of the deltoid musculature. We can see some of the fibrous nature, if you will, of the deltoid musculature. This is actually the subdeltoid, the potential space of the subacromial subdeltoid bursa. And here's the supraspinatus muscle itself. And here's the cortical surface of the humerus with the greater tuberosity. And we'll talk a little bit about why we don't see into that bone on ultrasound in a little while as well. So what determines the amount of that reflection that we see? Well, in ultrasound, impedance has this analogous, acoustic impedance is somewhat analogous to momentum. But rather than mass here, we're concerned about the density of the medium through which the sound passes. So acoustic impedance is given by this unit, kilograms per meter squared per second, called the RIL. And what determines that reflection? Well, in general, high density materials have high acoustic impedance. And if we've got two materials stacked on top of each other, which have very similar acoustic impedances, sound travels very easily from the one into the next one, okay? But when the acoustic impedances are quite different of those two materials, the sound does not travel very easily in between the two, and much more of the sound is reflected back to us. So it's that difference in acoustic impedance between those two that really governs that. So how do we calculate that? Well, how much percent reflection versus percent transmission do we end up with? Well, it turns out that if you have the acoustic impedances of the different materials. This equation, the difference between the two divided by the sum of the two squared times 100, will give you the percent reflectivity. So here's a nice table of acoustic impedances, right? And if you want to know how much is transmitted, you can just go ahead and subtract the percentage you get here from 100%, and that'll tell you how much sound is traveled through. So in this table, I've just put the acoustic impedance in Raels of some of the common things that we encounter so that we could make a couple of little calculations here. So what's the percent reflectance and the percent transmission at a soft tissue bone interface? So if you'll put in the acoustic impedance values from the table there, you'll find that about 43% is reflected and about 57% is transmitted into the bone. That's actually, the reflected component is a much higher component than we have at most of the soft tissue interfaces. So going from fat into muscle, let's say, or muscle into underlying liver. But notice that still it's about 50-50, right? 50 transmitted, 50 reflected. So you're probably wondering, well, still, why can't I see into that bone? And we'll get to that when we talk about absorption in a little while. We still make sure we scan between the ribs, right? Because we really get better transmission if we're not going through some bone. But this is a different situation than at air soft tissue interfaces. I mean, put in the numbers for air and soft tissue, and you see that 99.9% of the ultrasound pulse is reflected back to us. Soft tissue air interfaces really act like acoustic mirrors. They reflect all of the sound right back to you. We can't see anything beyond that depth because of all the sound that's being reflected back to us. And for that reason, I mean, if you guys have been in this situation, right? You're starting to scan some different areas and you're losing a little bit of your ultrasound gel, and all of a sudden you just don't see anything into the patient anymore because you've got a little air bubble between your transducer and the patient's skin. And the better contact you can get there with your gel, the better transmission you'll get into that patient. So here's the percent reflection from some of those interfaces. Like I said, notice bone soft tissue is nowhere near as bad as air. There's that issue of absorption we'll talk about. But look at how little is reflected at some of these. So notice what's going on as we do our ultrasound imaging. When we get to that capsular surface, let's say, of the liver, a small percentage of that sound energy is reflected back to us, and we detect that echo to make that border in our image. And then the majority of it's continuing through to strike another area and reflect some sound back so that we can see the next location, right? If this number was much higher, the ultrasound beam wouldn't penetrate very far before there was none of the original sound energy left to be reflected back. So here we are, right? We can look at some of these beautiful things we just talked about. Here's that nice reflective border at that surface between the subcutaneous fat and the surface of the liver. And right here's the boundary between that liver and the lung. And there's really nothing, if you will, but kind of noise behind that, because that's that acoustic mirror where all the sound ends up reflected back off of that surface. By the way, because all of that sound gets reflected back, it can really you can end up with some really kind of interesting pictures. And Bill Middleton, who I worked with back in St. Louis, was my attending when I was a resident. He loved to try and get some of these artifactual images whenever you had a patient. And so he has some of them in the book here. But think about it. You're imaging the liver. Sound is coming in. As soon as it hits that liver-lung interface, we talked about the fact it's all the sound gets reflected back. But this surface is curved a little bit, so some of this sound, right, gets reflected over towards where this lesion might be located. And then that sound reflects off of that lesion back to this acoustic mirror and back up to the transducer. But the transducer just thinks that that sound continued along the straight path we sent it out on. So it thinks that sound must have traveled this path and then had the sound come back. And all of a sudden you see a lesion in the center of that lung where you shouldn't be able to see something. So here's a nice example of that. Here's someone who's got a TIPS in place. Notice it looks like there's a TIPS up in their lung, and this is all the result of that lung acting as an acoustic mirror and the fact that the curved surface of that liver reflects some of that sound off at an angle rather than it coming straight up at 90 degrees to the transducer. So combining two of those ideas we just talked about. And sometimes you'll also see that manifest itself as a vessel, right? A vein on the inside the lung when you're doing Doppler at that liver-lung boundary. All right, so reflection and transmission, right? That beam encounters multiple surfaces. We talked about nice strong beam coming back, a small amount of it being reflected, the majority of it continuing on. Now another interface, a small amount reflected back to us, the majority continuing on, and that repeats itself, right? There's another type of reflector that I want to talk about, right? These specular reflectors, those are those nice smooth interfaces where the sound interacts with that surface at kind of 90-degree angles, if you will. But they're non-specular reflectors where the sound basically scatters away in all sorts of different directions. And this occurs when we have irregular surfaces or small little particles which have linear dimension equal to or smaller than the wavelength of the ultrasound beam. And this is why earlier on I made a little calculation showing you about what the wavelength of some of those ultrasound beams were. Do you remember we were in the neighborhood of what, 0.6 of a millimeter or so, right, for that 2.5 or 5 megahertz transducer in that range. So in the range of sub-millimeter kind of range there. So these are surfaces that look like this, but not just surfaces, but maybe small little clusters of cells or organized regions of cells, and they send small amounts of sound off in all sorts of different directions. This non-specular reflection, or this diffuse reflection, results in fewer echoes reflected back to the transducer because a lot of them don't head back in the direction of the transducer. But some do, and they're rather small, and they vary quite a bit. And this is what gives different tissues that we look at in ultrasound their unique kind of echo texture, right? The reason that the echo texture of the liver looks a little bit different, if you will, than the echo texture of the cortex of the kidney. So those non-specular reflectors, irregular surfaces, objects with wavelengths less than that of the transducer. Remember at 10 megahertz, we're at about 0.154 millimeters, and providing the echo texture in that image. The next thing I want to talk about is refraction. Okay? Refraction occurs to the transmitted portion of the ultrasound beam when the incident beam strikes at an interface between the two at an angle other than 90 degrees. And just like in optics, refraction with ultrasound follows Snell's law as well. Now, we talked about the fact that we're going to assume that sound travels a constant velocity in all the soft tissues we look at. We realize that while we assume that for purposes of making the ultrasound image, it's not in fact true. And so when we get these interfaces between these two objects, sometimes we'll see little artifacts in the ultrasound image because of this refraction, and I'll show you a copy of them, right? The truth is the velocity in the first media is not exactly the same as the velocity in the second medium, and when that occurs, we get a slight bending of this refracted ultrasound beam, and whether the angle, the amount to which it's refracted, depends on whether the velocity is higher than lower, and showing that here in these two pictures. But this is the reason why at the edges of something like a cystic structure, we get these bands of low intensity on the ultrasound imaging. Because the speed that the fluid travels in the soft tissues versus in the fluid are slightly different. But the only place we really notice this is where that sound ends up bent slightly right at that interface. So these little bands that we see right here are the result of refraction. There's some beautiful things, right? Some beautiful artifacts that occur because of some of the things that happen in ultrasound that we can see in this image. When ultrasound travels this path, it goes through some soft tissue and it's attenuated, and I'm going to talk about attenuation in a while. Fluid does not attenuate the ultrasound beam much at all. So the intensity of the ultrasound beam, when it gets to this area in the soft tissue, the beam that traveled this path is much higher than the beam that traveled this path to get to the same depth in the tissue. And for that reason, the reflected echoes from here are stronger, even though the tissue is exactly the same as that depth. So this appears more intense or brighter on our ultrasound image, something we refer to as posterior acoustic enhancement, a term that I'm not a huge fan of. And notice the shadowing beneath this structure is due to a completely different reason than that refraction that we were talking about. This is due to the nature of the absorption of this object to the ultrasound beam, and I'm going to talk about that in a little while when we talk about how bone, how calcium absorbs the ultrasound beam. So here we truly have a true shadow beneath that, shadowing beneath that object. Of course, because the ultrasound beam doesn't know that refraction has occurred, right? The assumption again is that the ultrasound beam is always heading off in this direction. When we get this little bending of it due to refraction, and then the echo comes back to the transducer, our ultrasound machine plots that echo as though it occurred during that straight line path that it was assuming. So that allows you to create some of these beautiful artifacts. So one of the nice places to make them occur is at the junction with the two rectus abdominis musculature. So notice you can get a beam that goes straight through and the junction between those and doesn't go through any of the musculature and hits the aorta. Then you can get some of your ultrasound that comes through, gets slightly refracted, travels to the other surface, slightly refracted again, and heads back down towards the same location. But your ultrasound machine thinks that this beam that it sent out continued traveling along this direction. So it plots these points in this location. And so in a real patient, occasionally if you'll center right over the rectus, you can make it look as though they have two aortas, an artifact again of this phenomenon here, a misregistration artifact. Diffraction also occurs with ultrasound. You know, although when we send out an ultrasound beam, we would really like it to travel along that thin pencil-like beam that we have it. As it goes deeper and deeper, it tends to diverge or to diffract. Excuse me. And this increases as the source of the beam gets smaller, so it's worse for some of our phased array lobes, and it affects the lateral resolution of our beam. So it doesn't affect our resolution axially as we head out, but notice the ultrasound wave, if you will, is getting wider, more spread out the further we get away. So our resolution properties in this direction, the lateral resolution, gets reduced. I want to mention the fact that ultrasound waves can interfere with each other. And when we think interference, we think primarily of destructive interference, where they kind of cancel each other out. But also there's constructive interference, and we use that to our advantage. On these small phased array transducers, I'm going to stimulate different elements on that array to kind of create pairs and multiple, more than pairs, multiple ultrasound waves that constructively interfere with each other to steer the ultrasound beam, if you will, in a direction that we want to look. I mentioned the fact that absorption occurs, and this is frankly how some of the therapeutic ultrasound works, where basically our goal is to dissipate this ultrasound energy by moving things back and forth in the tissue, and that energy gets deposited just heating the tissue there. So if we look at an ultrasound wave, some of the tissue just ends up absorbing some of that energy, if you will. What affects that absorption? Well, the frequency certainly does. The higher the frequency, the more absorption of that occurs. Certainly the viscosity of the material affects to some degree on how that helps. And so does the relaxation time. You know, how much energy does it take to get those particles moving back in the opposite direction? Because remember, as sound propagates, it's got to be able to basically move those molecules back and forth. So next thing I want to talk about is attenuation. And this is the overall effect of scatter and absorption has on the X-ray beam. Okay? And it really is the major determinant of the depth of beam penetration, how far the beam can go in and we still have enough useful signal coming back to us to make an image. We can't measure every interaction that the beam makes with every particle hits, but we can make the assumption that penetrance is inversely related to the frequency of the beam. And this is why we use high-frequency probes for looking at the liver surface, but not looking deep like at the renal arteries. As an MSK radiologist, we're looking at superficial tendinous and ligamentous structures. We like a very high frequency transducer, but for the abdominal imaging, you know, we end up going a little bit lower. One thing you realize, right, that if boundary 1 and boundary 2 are the same, the echo that we're going to hear as we come back to the transducer is still going to be different. Because here, our echo is going to be a proportion of this ultrasound beam that's transmitted. But echo 2 is only going to be this strength, because while the same percentage of the ultrasound beam may be transmitted, the ultrasound beam that's hitting it is less than the one was before. So we do what we call time gain compensation, those sliders that you have on the side of your beam. And basically what that's saying is, I want you to electronically increase or amplify the signal as a function of depth. So that if we were looking at uniform interfaces, kind of equally spaced at different depths in the tissues, they would appear to be the same, rather than getting fainter and fainter as we went deeper with depth. Here's a nice 5 megahertz transducer. Notice you can't even see the IVC here because of the attenuation of the beam is so great, you're really not seeing structures there. Going to 3 megahertz, notice we've got a much better depiction of that there. And again, this linear thing on the side is always depicting where we've got our time gain compensation sliders in position. So what are some of the attenuation coefficients? How many decibels per centimeter of tissue do some of these different structures decrease the intensity of the sound beam? The first thing I want you to notice, the first one on there, white, water really does not decrease the intensity of the sound beam at all. Water doesn't really attenuate the sound beam much at all. And now you understand why we have that quote-unquote posterior acoustic enhancement when we have a cystic structure, right? The ultrasound beam just is not attenuated very much by fluid. Notice how much bone attenuates the ultrasound. So remember I said before, at that surface of the bone, about 50% of the sound is reflected and 50% is transmitted. But the problem is that 50% that's transmitted is very quickly attenuated by the bone. And so therefore we don't see much inside the bone at all. But it's for a slightly different reason than we don't see inside the lung, where nearly 100% of the sound was reflected at the soft tissue lung interface. Okay. Let's utilize these numbers a little bit to kind of make a couple of maze, right? So here's the frequency of our transducer. We're going to go from a 1 to a 2 to a 5 to a 10. Attenuation coefficient per decibel per centimeter, 0.5, 1, 2.5, and 5. So how much intensity reduction do we get traveling through 1 centimeter of this soft tissue? Well, 11%, right? 21% for the 2 megahertz, 58% for the 5 megahertz, and 68% for the 10 megahertz. So you can see that, right, with these high frequency transducers, it becomes much more challenging to image in the depth. And here is the reduction for traveling 10 centimeters deep. And you can see, right, there's no way you're getting any information 10 centimeters deep in this soft tissue using a 10 megahertz transducer. So again, that brings us back to this image once again, and again, just talking about why we don't see anything deep to the surface of that bone. Here's another nice picture in that regard, right? Here we've got all those stones located, right? They're calcium. Remember how much that calcium, just like bone, attenuates the ultrasound beam. So with those stones layering in the gallbladder, notice your ability to see anything deep to those is really completely non-existent. If we'll go ahead and have the patient roll over to get those stones to roll into a different position in the gallbladder, we can now see that the structure is sitting deep to that very nicely. I already mentioned the notion of posterior acoustic enhancement, the fact that with this cystic structure, the tissue deep to it appears slightly brighter, even though it has exactly the same properties as the tissue next to it. And that has to do with the fact that the ultrasound beam that travels through there gets less attenuated than the ultrasound beam that travels this path. So let's talk a little bit about image quality, right? We use the same transducer to transmit and receive the sound signal in ultrasound. So let's discuss those functions as though they're completely separate from each other, and discuss how we're going to form that image, and talk a little bit about some of the measurements of image quality. So the transducer is made out of this piezoelectric crystal material, right? And if I apply a voltage to that, a voltage across it, it deforms that crystal, it changes its shape, if you will, just like a speaker. As we apply that voltage, you know, the cone in that speaker moves in and out, if you will. The same thing, this piezoelectric crystal is going to change its shape. So we're going to use that to apply that voltage at a particular current, at a particular frequency, to deform that crystal and propagate the sound. After that occurs, we're actually going to listen with that crystal, and as sound waves come back and hit the surface of that crystal, they're going to deform the crystal and create a voltage across the crystal that we'll be able to measure. So transmission gain, right? If we turn up the transmission gain, that changes the voltage across that crystal and allows us to produce a more intense ultrasound beam. We're not talking about the frequency. The frequency is a different setting. We're talking about the intensity of that ultrasound beam. Okay? So we end up with a stronger transmitted signal and consequently a stronger received signal. The receiver gain increases the amplitude of the signal returning, but it basically is electronically amplifying the received signal. The time gain compensation sliders are doing that. It's increasing the returning signal there. Ideally, for each pulse, we'll have this short packet of ultrasound energy that's of the appropriate frequency to direct into the body. In truth, we get this amalgam of frequencies that kind of are centered around that center frequency that we want. It's very difficult to create a pure single frequency ultrasound pulse tone to send in the body. Tissue harmonic imaging, it turns out that as sound travels through the body, we end up getting harmonics, which are integral multiples of frequency of the center frequency of the beam. That transmitted beam interacts with tissues emitting those harmonic frequencies. And it turns out we can set the transducer to listen to the harmonics, to listen to the higher frequency harmonics, rather than the original frequency of the ultrasound beam. And what's nice about that is it gives us a little improved contrast resolution. we get a little bit better noise properties because there are less things that are occurring up at that frequency. Gives us some improved lateral resolution and some reduced artifacts. So a lot of times we use some of the tissue harmonic imaging for that. Side lobes, when we end up trying to create this single focused line of ultrasound heading off in just one direction, just like creating an ultrasound pulse of a single frequency is nearly impossible. It's nearly impossible to create that sound heading off just in one direction without creating some sound heading off in some other, slightly other directions as well. And those are referred to as side lobes. They're secondary projections of ultrasound energy that radiate away from the ultrasound beam. There are a number of reasons why they occur, and I don't necessarily want to get into those, but realize we can end up hearing reflections back from them and misinterpreting that returning echo as occurring along the direction of the beam that we sent out. And so there are some side lobe artifacts that occur from that. Our transducer, it can't, right, we're going to use it both to send out our ultrasound and then also listen. So what we need to, we can't do both of those things simultaneously. So what the transducer does is it sends out a short pulse, a short chirp of a few cycles of the ultrasound pulse at that frequency, and then it waits and listens for sound to come back. And then after it waits an appropriate amount of time, let's say enough time for that sound to have traveled the 10 centimeters deep into the body that we wanted to look and back to the transducer. Once that time is over, it's now time to send out another pulse of ultrasound in a slightly different direction. And that time interval between those two is what determines the pulse repetition frequency, or the number of pulses per second. That pulse repetition frequency, right, is limited by the maximum depth to be sampled and by the acoustic velocity, right? I mean, if I want to see a particular depth in the tissue, then I have to wait until my sound travels that distance and then back to the transducer before I start with my next chirp, just like I talked about. The machine usually sets the pulse repetition frequency according to the depth selected by the operator. So when I say to the tech, hey, go ahead and decrease the depth there, the machine now knows that I can increase the pulse repetition frequency because people aren't interested in looking at the echoes that are coming deeper than that. So what is the maximum pulse repetition frequency if we want to look 10 centimeters deep? Well, here's our value for C, right, that 1,540 meters per second. Remember, if you want to go 10 centimeters deep, that's 1/10 of a meter, so we'll get those in the same units. And I've got to give enough time for the sound to travel 10 centimeters into the tissue and the echo to travel 10 centimeters back. So we've got a factor of 2 here to multiply by that distance. So my pulse repetition frequency is 7,700. So I can send out a line of ultrasound information 7,700 times a second. Now, if it takes me about 100 lines of ultrasound to make one image, that means that I can make about 77 images per second, okay? And we'll talk a little bit about that in a little while. So here's that is, right? Here's that short chirp of ultrasound energy that we're sending out. And then we're waiting and listening to it before we send out our next chirp along a slightly different direction. And the time between these two things, that's our pulse repetition frequency. The frequency of this wave, that's the frequency of the transducer, that 1 megahertz or that 10 megahertz. And remember, we send out more than just one wavelength, more than just one cycle, because when we're in the listening mode, we actually have to hear about a cycle or 2 or 3 returning as an echo to understand that what I'm hearing is the same frequency sound being reflected back to the transducer. So we send out a few of those, typically in the order of 3 cycles of that sound. The spatial pulse length, right, that longitudinal length of the pulse, right, that longitudinal length of this pulse right here is equal to that wavelength of the pulse times the number of cycles emitted. So I just told you around 2 to 3. That's usually what determines our resolution, right? So if we have a 6 megahertz transducer, a 6 megahertz transducer has a wavelength of about 0.257 millimeters, and now if I have to send out 3 cycles of that, those 3 times that is equal to 0.857 millimeters. And that's really going to be the predominant determinant of my resolution along the direction of the ultrasound beam, right? Does that make sense, right? I've got to be able to hear that pulse coming back to me. I can't resolve 2 surfaces being separate from each other much more than that amount, that 8.57 millimeters there. All right, as the sound energy produced by the transducer interacts with those surfaces in the body and parts of it gets reflected back, that strikes the face of the transducer, and we convert that deformation of the piezoelectric crystal gets converted to an electric signal. Right. That signal is amplified, processed to being process for the display. Remember, we're amplifying it based on the depth that it went, knowing that we have to compensate for the amount of tissue that the ultrasound beam might have traveled through. So let's talk a little bit about our resolution, because, you know, when we talked about X-ray imaging, we mentioned the fact in CT imaging, our resolution is best at the center of the image, and it decreases as you go out radially from that. Ultrasound is kind of a similar kind of thing where our resolution along the direction of the ultrasound beam is very different than our resolution lateral to that. So our axial resolution and our lateral resolution we want to talk about. So axial resolution is how close together 2 objects can be along the direction of the beam, and we can still detect them as being separate. And I've just mentioned that in great part that is related to this spatial pulse length, our wavelength times the number of pulses that we sent out. Because that spatial pulse length itself is determined by the frequency of the transducer, the frequency of the transducer plays a major component in what our axial resolution is. So higher frequency means a shorter spatial pulse length and means we've got better axial resolution. Of course, there's a trade-off there, right? We've already talked about the fact that the depth at which we can image gets much less the higher the frequency of the transducer goes. So here we go, right? We've got our, here we're set at high resolution, right? And here we're set for high penetration. And again, you'll notice in terms of the resolution of these structures deep, using a higher frequency transducer, right? Higher frequency setting on that transducer, we can separate those objects a little bit better with more depth. Now, what determines that lateral resolution? The resolution kind of, if you will, in that arc that's perpendicular to the axial resolution. Well, this is really the ability to resolve those 2 objects adjacent to each other, perpendicular to that beam axis, and frankly depends upon the number of lines we want to use to make up a single image in the scan. A narrower beam width correlates with improved lateral resolution. And as the beam fans out, that lateral resolution worsens. So, you know, unfortunately, as we go further into the object, the resolution in the lateral span gets worse, right? Especially when we've got these curved array transducers. Just think of your lines of sound coming out. As you get further away, those lines are getting further apart from each other, farther apart from each other, and our resolution is going down laterally. We can improve that lateral resolution a little bit by purposely focusing the ultrasound waves at a particular depth. In other words, we want to make sure that they're staying fairly close together up to a certain depth. And remember, I told you we could use the constructive interference of the different ultrasound waves to create a wave which is kind of most focused at a particular depth in the patient. So by adjusting the pulse timing, we can get the ultrasound to focus to its best lateral resolution at a particular depth. And in fact, you guys are familiar with this, right? Because you've got this little depth of focus indicator on the side of your ultrasound image, and you've noticed that if it isn't at the proper location, you get a much poorer quality image than when you put it at the appropriate depth. We'll talk a little bit about the mode of transmission of ultrasound. A-mode ultrasound, it's a good historical model in explaining some of the ultrasound physics. It's referred to as amplitude mode. We send out a single pulse of ultrasound into the body, interacts with those interfaces, and the echoes are detected. The image is just a plot of the amplitude of the detected signals as a function of time. So something like this, right? Not tremendously helpful. M-mode is motion ultrasound, so similar to M-mode, except that the image is a one-dimensional line, right? Is a one-dimensional line with the amplitude of the echo corresponding to the brightness on the line. So think about that. That would be a single line from your X-ray image being displayed. And sometimes we'll take that single line and we'll display that line over and over as a function of time, as done in the bottom of this cardiac study. Or the other thing that would be possible to do is if you had an M-mode ultrasound, you kind of have a pencil that gives you a line of ultrasound. If you had persistence on a monitor, you could sweep that line of ultrasound across the object and kind of trace out an image from that. But in our current mode of real-time scannings, right, we get this image continuously formed as this beam is swept across the field of view for us. Only objects on the scan line are depicted at any given moment. Multiple scan lines form the field of view. The two-dimensional image is a representation of the reflectivity of the structures within the field of view during the time at which it took to sample all of the lines in the field of view, right? Which may have taken a few hundredths of a second to do that. So it's not instantaneously acquired all at one time, right? First one line, then the next line, then the other 98 lines that make up that single ultrasound image, and that's displayed. And then those lines start to update each other and are replaced as we go through with that. Multiple scan lines compose each image, as we talked about. One pulse of the beam is needed for each of those scan lines, so the time needed for each beam to enter the tissue, interact, and return to the transducer determines how often we'll be able to update the image, right? The deeper that we want to look into an object, or the higher number of scan lines you want, the longer it's going to take you to get a single image there. And remember, 13 milliseconds per centimeter of soft tissue times the number of scan lines is the rough number that you'll end up with. And that's just by taking the sound, doing some of the calculations that we talked about before. You can break it down to that. So how can we decrease the scan time, right? You can decrease the depth. So if you're only looking at something that's fairly superficial, right, decrease your depth, you'll get much better temporal resolution. You'll get many more frames per second. You could decrease your number of scan lines, and unfortunately that sacrifices your lateral resolution, right? It's really your scan line density that determines your lateral resolution. The other thing is you could increase your pulse repetition frequency, but this really is just a restatement of the first way, since there's an inverse relationship between that pulse repetition frequency and the depth that we can see there. But let's just do a quick frame rate calculation. The maximum frame rate is the speed of sound divided by 2 times the depth that we want to look at times the number of lines that we want to scan. And if you'll notice that this quantity right here turns out to be related to the pulse repetition frequency, and so you can also express that as just being the pulse repetition frequency divided by the number of lines that you want to scan. So what if we want to go 10 centimeters deep and 100 scan lines? I think I've been speaking about this example, so I don't think the answer is going to surprise anyone. Remember, we did this calculation before where instead we just talked about imaging 10 centimeters deep, and we found out that we could image lines at about 7,700 hertz, 7,700 hertz, and I said, well, if you want 100 scan lines in an image, your frame rate will be about 77 frames per second. What if our depth increases to 20 centimeters? Well, now it's going to take twice as long for us to sit and wait for echoes as sound propagates the additional 10 centimeters in and the additional 10 centimeters back out. So our maximum frame rate is going to drop in half, not surprising. Some different types of transducers: mechanical transducers, linear arrays, curved linear arrays, some phased arrays. Not a lot of mechanical transducers out there. Some of these old sonocyte transducers actually mechanically rotated the ultrasound transducer back and forth in them and sweeped it through that. The frame rate is somewhat limited by the motor speed in which it's rotating that, and I said sonocyte, I meant to say site-right transducers. Here are the linear array transducers. We use them a lot for musculoskeletal, multi-element transducer array, crystals aligned in a straight row. They're activated sequentially to form scan lines. You can activate some of these in groups to get some sort of steering to the beam if you want. And here's that scanning motion for that linear array. Again, operating, if you want, you can fire multiple in a way that they interfere constructively, so you get them focusing at a particular depth if you want. When we see an ultrasound study done with the linear array, it's usually very obvious because the face plate is straight right across the front. And the one thing I wanted to point out to you in terms of the linear arrays is that our loss of resolution as a function of depth is less than it is for the curved linear arrays where the ultrasound beams are diverging as they get further away from each other. Here they're parallel to each other. They do still tend to spread out, to diverge a little bit, right, in terms of the ultrasound beam, but not nearly to the extent on those curved arrays. So here's that curved ray. It's another multi-element transducer where they're arranged in an arc instead, typically a little bit lower in frequency. And again, we can usually tell that we're using one of those transducers in that we see this curved surface at the top of the image where we're looking at the object. And here's that linear phased array. Now we've got this two-dimensional array of piezoelectric crystals that we can really fire in very unique combinations to really steer the beam in a lot of different directions. So it allows us to have a transducer with a really small footprint, which is great for kind of seeing between the ribs, those kind of things, and still being able to sweep the ultrasound beam out at different angles. Remember, these lines really diverge with depth, and therefore we don't get that density, uniform line density, and our spatial resolution drops off quite a bit in that lateral direction as that occurs. And usually we can recognize them because you'll notice at the top of the image you have this really small footprint from which the ultrasound image appears to be arising. And like I mentioned, these really utilize that constructive and destructive interference we talked about, timing the pulses on the different piezoelectric crystals in the 2D footprint to steer the beam into the different directions we want it to head. Just briefly talking a little bit about Doppler, right? Moving objects result in change of frequency from the ultrasound source. We're all familiar with kind of the Doppler effect. And we know how that change in frequency relates to the velocity of the object that's either coming towards us or moving away from us by that simple equation there. If the moving object's at an angle theta with respect to the transducer, then the frequency shift gets multiplied by this cosine theta term here. And the importance of that is there's no shift. No shift ends up detected when the transducer is at right angles with respect to the direction of flow. So if we want to get good Doppler estimations of flow, we really have to make sure that we're away from this 90-degree angle in doing that. All right, so here's our transducer sampling the flow in that blood vessel there. In pulsed wave Doppler, the transducer alternates between the transmission and reception, right? Doppler information sampled from only a small sample volume. We typically define that as some subregion on the image. And it's presented overlaid right on top of our grayscale image. I'm sorry, actually, that's in color Doppler. We get some really good resolution in that sampling volume. We get the analysis of multiple vessels at different depths when we do that. It's looking along that single line. And the disadvantage is that susceptibility to aliasing. In color Doppler, we're now going to show the direction of flow relative transducer based on average velocity. So red flowing towards the transducer, blue away from it. It allows us, we look at some little subregion inside the grayscale image typically. It allows us to quickly identify normal, abnormal flow, whether it's towards the transducer or away from it. Visualization of some small vessels is improved versus pulse wave Doppler. And limitations, we've got lower spatial resolution than the grayscale. It's really not very sensitive to slow flow, also susceptible to artifact, and of course it takes a lot of time, so we get lower our temporal resolution. With power Doppler, we get a good signal regardless of the direction of the flow. And it's presented as typically this kind of hot iron overlay of the B mode image. And it's very sensitive to low flow. It's independent of the Doppler angle, so we higher gains possible, and there's no aliasing there. But the limitation being, right, there's no direction or velocity information obtained from that. Very sensitive to transducer or patient motion. And again, we've got that low temporal motion, right? That aliasing occurs when the Doppler shift frequency is higher than the Nyquist frequency limit, right? So we're not sampling fast enough to see the velocity of that flow. And the appearance is always fairly straightforward, where the top portion of part of this pulse is actually wrapped around to the bottom aspect on the image of the flow.